Hello students, we have seen stereochemistry in last video. In stereochemistry, we were discussing about basic terminologies like chirality, asymmetric carbon and optical activity. Some more terminologies of stereochemistry are left. So today we are going to discuss some more terminologies of stereochemistry. Okay, so first terminology is retention. Okay, the word itself suggests that there is retention of position of any atom or group. Let's understand this by one example. Okay, so you have got asymmetric carbon over here. Four groups are different, and as we know, if four groups are different, then that carbon is known as asymmetric carbon. Here, in this reaction, substitution reaction has taken place. So we have substituted X with Y. So here, in case of X, there is substitution of Y, right? But if you look at the reaction carefully, you can see that X is replaced by Y, but the position of X is not changed. I mean, the position or configuration remains same. Uh, I'm saying position, which means suppose this is carbon. Here A is there, here B is there, here C is there, here X is there. Now X is replaced by Y. But this position where X used to be there, the position is same. Substitution reaction has taken place, but the position remains same. The spatial, which means arrangement of atom in space remains same, which means X is replaced by Y, but this position, I am talking about this position is not getting changed. This position is remaining same. So we can say that retention has taken place. So there is retention of atom, there is retention of spatial configuration, there is retention of position. So substitution reaction has taken place, but the position remains same. So that kind of reaction is known as retention. Now let us understand retention with one more example. Okay. So we have got 2-methyl-butane-2-ol. So we can say that 2-methyl-butane-2-ol. So 1, 2, 3, 4. Carbon number 2 is having methyl group, and at first number carbon OH group is there. So this is 2-methyl-butane-2-ol. Now we have written hydrogen like this, which means that hydrogen is far away from the observer, right? So hydrogen will be far away. Now it reacts with HCl in presence of heat. We are providing heat. Now OH group is replaced by chlorine. So OH group is replaced by chlorine. So H from acid, OH from this reactant, HOH will form H2O. Now Cl will substitute OH. So instead of OH, there will be chlorine group. So substitution reaction has taken place. Chlorine has replaced OH group. But if you see, the position of OH is remaining same. The position is not getting changed. The spatial arrangement, the arrangement of atom in space. So OH used to be here, but after substitution, Cl is also in that position only. The position is remaining same. Although substitution reaction has taken place, Cl has replaced OH, but this position, I am talking about this position is not getting changed. The position of OH, the position of atom, the position of this configuration is not getting changed. It remains same. So we can say that retention reaction has taken place. So retention means although there is substitution, but arrangement of atom remains same. The atom which used to be earlier at that carbon, at that configuration, after substitution, arrangement is not getting changed. Configuration remains same, right? So that is known as retention. Okay. Now we are going to discuss inversion retention in detail with one more example. Okay, so our next topic is inversion. We have already seen retention and we are going to discuss racemization. In last video also we have discussed about racemization. Okay, now let's understand this phenomenon by this example. Okay, look at structure. So here C2H5, hydrogen is there, CH3 in X. Now understand this sign. If dotted line is there, which means atom is away from the observer. If solid line is there, which means this atom or molecule is towards observer, right? The person who is observing, the molecule is near that person only. This line, this dash line indicates these atoms or molecules or these functional groups are in one plane only. Okay. Now, here substitution of x has taken place by y. So x is replaced by y. But if you see the position of x remains same. Although substitution reaction has taken place, x has been replaced by y, but the y is at the same position where x used to be, right? The position of x is not getting changed. So y has replaced x, but the position remains same. So we can say that for compound A, retention has taken place. So if there is no change in position, so we can say that it is retention reaction. Now look at this reaction. Here substitution of x has been done by y. So instead of x, y has come, right? But the problem is the position of x is getting changed, and which is opposite to the y, right? So x used to be here in that position, but y is opposite to that position, right? X is in this direction, x is in this position, but the position of y is different. We can say that it is opposite to the position of y. So we can say that it is inversion. Inversion means the atom is substituting another atom, but the position is opposite to previous atom. So x is there, but after substitution reaction, y is position in opposite to x. So there is inversion of position. So position of x is opposite to position of y, right? So if opposition, I mean we can say that opposite direction has come, then we can say that inversion has taken place. Now in some cases both type of reaction has taken place, both type of reaction takes place, then we can get both products A and B. A is retention, B is inversion. So we get 50% A and 50% B. Then we can say that racemization has taken place. That is known as racemization, because we are getting 50% A, 50% B. So we are getting equal amount of the mixture of A and B. So racemization has taken place. So racemization is equal amount of this retention and inversion product. Now the optical activity of this mixture A and B would be 0. There is no optical activity because we are getting equal amount of both the products, equal amount of A and equal amount of B. So we are getting same in retention and inversion in equal amount. So there will be no optical activity. So remember this for MCQs. For racemic mixture, optical activity is 0, which means that if we transmit light from the solution of this racemic mixture, light will pass straight line, it won't get rotated, right? So optical activity of this racemic mixture would be 0. Now we'll understand this terminology in context of SN1 and SN2. So let's discuss this in detail. So we are going to discuss inversion and retention with context to SN1 and SN1 and SN2 reaction. So first of all, we will discuss SN2 reaction. Okay. So we have got 2 bromo-octane over here. This is 2 bromo-octane. Bromine is at carbon number 2 and total 8 carbons are there. So this is 2 bromo-octane. Minus sign indicates that it is levorotatory. It rotates light in left direction. Okay. Now, nucleophile is OH minus, which means 2 bromo-octane reacts with NaOH, strongest base NaOH. So OH minus is a nucleophile. Now, nucleophilic substitution reaction will take place. So instead of halogen, nucleophile will come. Now, so halogen has been replaced by nucleophile, which is OH minus. But if you see the position of halogen and OH minus, so Br minus used to be present here, but OH minus is opposite to that Br minus. So again, we have already seen about retention and inversion. The position of Br minus is in this direction, but after nucleophilic substitution, OH minus is in opposite to the Br minus. So if atom or functional group comes in opposite to the previous atom which was getting replaced, we can say that inversion has taken place. So here SN2 reaction, inversion has taken place. So what is inversion? So inversion is nothing but if any group or atom replace another atom, but the new atom is in opposite direction to the previous atom, we can say that inversion has taken place. So OH minus is in opposite direction to Br minus. Br minus used to be here, but OH minus is there, right? So OH minus is opposite to Br minus, so we can say that inversion has taken place. So in SN2, we can say that inversion is going on, right? So inversion is happening in SN2 reaction. Now let us see what will happen in case of SN1 reaction. Now let us discuss retention inversion for SN1 reaction. Okay, so let us understand this by one example. So we have got 2 bromobutane. This is bromine at carbon number 2. Total 4 carbons are there, 1, 2, 3 and 4. So this is 2 bromobutane. Ethyl group is towards observer. Hydrogen is away from observer, right? Bromine and methyl groups are at planar, at one plane only. Now, as we know that in SN1 reaction, first formation of carbocation is taking place. So first step is formation of carbocation. So in protic solvent, there will be release of halide ion. So bromine is released, and after release of bromine, there will be formation of carbocation. So in first step, carbocation is formed. Now, after formation of carbocation, OH minus or any other nucleophile will attack on carbocation, right? Now, here 2 possibilities are there. After formation of carbocation, 2 possibilities are there. OH minus, which is a nucleophile, can attack on carbocation at any position, at any configuration. So OH minus can attack from this side or OH minus can attack from this side. So suppose if OH minus attack carbocation from this side, then we will get product like this. So here OH will come at this side. So there is retention of position of OH. Br used to be here at this position and OH is also remaining at that position. So we can say that if OH minus or nucleophile can attack from this side, then there is retention is taking place. But what about OH minus from this side? So if OH minus attack carbocation from this side, then we will get product like this. So OH minus is in this position. So Br is used to be in this position, whereas OH minus is opposite to that position, opposite to the Br minus. So here we can say that inversion has taken place. So this is retention, this is inversion. Now we have already seen that if we are getting two products, a mixture of retention and a inversion, then we can say that racemization has taken place. So that is nothing but racemization. So racemization is a mixture of two products, retention and inversion. So we are getting two products in SN1 reaction. The reason is here carbocation formation is there. Now after formation of carbocation, any possibility is any possibility of OH minus can come, right? So OH minus can attack from this side or OH minus can attack from this side. So two possibilities are there. In one possibility, retention is taking place. In another possibility, inversion is taking place. So we are getting mixture of retention and inversion product. And as we have discussed, if we are getting mixture of retention and inversion product, that is known as racemization. And as we know that the racemic mixture has no optical activity because this is a mixture of 50% levorotatory and 50% dextrorotatory. So we are getting equal amount of dextro and levorotatory. So there will be no activity, there will be no optical activity. So optical activity of this compound would be 0. So we can say that after SN1 nucleophilic substitution, the mixture we will get is optically inactive. So we have discussed SN1 and SN2 in context of retention, inversion and racemization. So the moral of the story or conclusion of this topic is in SN2 reaction, in nucleophilic substitution reaction 2, inversion is taking place. But in case of SN1, we are getting equal amount of retention inversion product, and that terminology is known as racemization, and the optical activity of this racemic mixture is 0. So we can say that after SN1 reaction, the mixture which we are getting, the optical activity of that particular mixture is 0, right? So this is all about retention inversion in context of SN1 and SN2. Okay.